What if the first quantum computer was not a machine at all, but a complaint about machines? In 1981, Richard Feynman identified a strange mismatch at an MIT conference. Ordinary computers were built from digital switches, while nature itself followed quantum rules. The problem was not simply that calculations were difficult, it was that the language of the calculator did not match the language of the universe. A conventional computer stores information in bits. Each bit is represented as a 0 or a 1, and every calculation is constructed from operations that manipulate those definite values. That architecture is extraordinarily powerful for arithmetic, communication, and logic. Yet when it tries to reproduce a quantum system, the description can become overwhelmingly large, because the system may occupy many possible states at once. Quantum mechanics describes matter through probabilities, wave-like behavior, and relationships between particles that have no simple classical equivalent. To simulate those features with ordinary bits, a computer may need to track an enormous collection of possibilities simultaneously. Feynman saw the paradox clearly. The closer the simulation came to nature, the less naturally the classical computer seemed suited to the task. His proposal was radical in its simplicity. Rather than forcing a conventional computer to imitate quantum behavior from the outside, why not build a computer from quantum systems themselves? Its information units would not be ordinary bits. They would be quantum bits, or qubits, physical systems capable of representing quantum states and being manipulated according to quantum rules. That distinction changed the question. The challenge was no longer merely how to make a faster calculator. It was how to define computation when the underlying information could behave unlike any information system humans had previously engineered. Feynman had identified the pressure point, but identifying a new machine is not the same as defining what that machine can do. The missing step belonged to David Deutsch. Where Feynman exposed the simulation problem, Deutsch sought a formal framework, a precise description of a universal quantum computer. Universal means capable, in principle, of carrying out any computation that can be expressed through an appropriate sequence of operations, rather than being designed for only one special task. This was a conceptual transformation. A quantum computer would not be a mysterious device that somehow tried every answer at once. It would be a programmable system governed by quantum mechanics. Its power would come from preparing qubits, applying carefully chosen operations, and measuring the resulting state with the calculation arranged so that useful patterns became more likely to appear. The qubit itself is easy to describe and difficult to control. A classical bit must be 0 or 1. A qubit can occupy a superposition, meaning a quantum combination of those alternatives before measurement. That does not mean a person reads out every possibility as a separate answer. Measurement produces a definite result, and the art of quantum computing lies in shaping the probabilities before that moment arrives. Another principle deepened the mystery: entanglement. When qubits become entangled, their joint state can contain correlations that cannot be reduced to independent descriptions of each qubit. The information belongs partly to the relationship between them. A universal quantum computer would therefore manipulate not only individual units, but carefully organized patterns of possibility. The early prototype was an idea on paper. There were no practical quantum processors waiting to demonstrate the concept, no mature architecture, and no established engineering recipe. Yet a formal model can be a kind of prototype. It specifies what the machine must be able to represent, how its operations should work, and what counts as a legitimate computation. That abstraction mattered because it separated the essential idea from any particular hardware. A qubit could be realized in different physical systems, but the computational principles would remain recognizable. The machine might eventually use one kind of quantum object or another. The definition came first, creating a target for experimentalists who did not yet possess the tools to reach it. The engineering obstacles were severe. Quantum states are delicate. Interaction with the surrounding environment can destroy the relationships that make quantum computation possible, a process known as decoherence. Errors can arise from imperfect operations, unwanted disturbances, or measurement itself. The first vision therefore contained a built-in warning. The same physics that offered new computational possibilities also threatened to erase them. This is where the origin story becomes unexpectedly human. Feynman did not present a finished technology. He posed a problem that exposed the limits of an existing one. Deutsch did not simply repeat the proposal, he translated the challenge into a formal machine concept. Between them, the field gained both a reason to exist and a language in which its claims could be tested. Their sequence also reveals why scientific revolutions often begin indirectly. The goal was not initially to replace every computer or accelerate every program. The pressure came from physics itself. If researchers wanted to calculate the behavior of quantum systems, they needed a computational framework that did not treat quantum behavior as an inconvenient exception. That insight redirected attention towards simulation. Molecules, materials, and other quantum systems are naturally described by quantum mechanics. A computer that could represent those systems more directly might help scientists investigate problems that resist ordinary calculation. The promise was not magic speed in general. It was a better alignment between the structure of the problem and the structure of the machine. Yet alignment alone could not guarantee usefulness. A quantum computer still needs an algorithm, a sequence of operations designed to transform an input into a measurable output. Superposition creates possibilities, but interference determines how those possibilities combine. Constructive interference can strengthen useful outcomes, while destructive interference can suppress others. This made quantum programming fundamentally different from simply adding more processing power. The programmer must choreograph probability amplitudes, the mathematical quantities that describe quantum possibilities, so that measurement reveals something valuable. The computer does not hand over an invisible collection of parallel answers. It performs a controlled physical evolution whose final statistics encode the result. For years, the most important achievement was therefore not a spectacular calculation. It was the existence of a coherent definition. Feynman's question had become a research program, and Deutsch's universal quantum computer gave that program boundaries. Researchers could ask which operations were possible, which algorithms might be efficient, and which physical systems could implement the required behavior. The broader computer science community eventually inherited a new vocabulary. Bits remained indispensable, but qubits introduced a different information model. Logic gates acquired quantum counterparts. Computation became inseparable from the physics of measurement, reversibility, noise, and observation. The computer was no longer treated as an abstract box floating above nature. Its physical substrate had become part of the theory. That connection carries a subtle consequence. Every computer is physical, but classical computing often allows engineers to ignore much of the underlying physics. Quantum computing makes that concealment impossible. The machine's behavior depends directly on phenomena that engineers must preserve, isolate, and control. The boundary between software and hardware becomes unusually thin. The old simulation problem also points toward a larger lesson about innovation. Feynman's insight was not that classical computers were obsolete. It was that a successful tool can still be the wrong tool for a particular universe of problems. Deutsch's contribution was not to abandon computation's foundations, but to ask how those foundations should be rebuilt when information obeys quantum law. That question continues to shape the field's ambitions and its caution. Quantum computers are not guaranteed solutions to every difficult problem, and quantum effects do not automatically produce useful answers. Their potential depends on algorithms, error management, physical control, and the exact structure of each task. The promise is powerful precisely because it is specific. The first conceptual machine also explains why quantum computing can feel both ancient and futuristic. Its ingredients are the fundamental behaviors of matter, studied long before practical quantum processors existed. Its objective is deeply modern, to engineer those behaviors into a programmable information system. Between those poles lies the entire difficulty of turning a physical theory into technology. Feynman saw that nature might be the best simulator of nature. Deutsch showed how that intuition could become a universal computational model. One supplied the unsettling question, the other supplied the disciplined definition. Neither began with a polished device. The genesis was smaller, stranger, and more consequential, a mismatch between bits and reality, followed by the decision to take that mismatch seriously. Quantum computing was defined at the moment. Computation stopped being merely an abstract manipulation of symbols and became a physical conversation with the quantum world. The machines came later. The decisive invention was the idea that the universe's own rules might not only complicate calculation, but provide its most powerful new foundation.